So, welcome to our first class on calculus with code. So, um, first let's make some setup so that we're going to work with it subsequently. So, we're going to start with Python. So you get to see it's actually things are a lot easier and maybe quite more interesting with Python than it is, I think, with MATLAB. But let's see. I don't know. You might see differently. So when we get there, you decide for yourself. But we're going to start with Python today. So let's see how it goes. And so this is Google Chrome browser. So this is what I recommend that you use. Just open your Google Chrome browser, and then if you're using someone else's laptop, if you don't have one, you want to use your friend's laptop to follow these classes, you can easily set up a profile for yourself on your friend's laptop so that things will not be mixed up. I mean, you won't have to save anything on your friend's laptop. It will just be on your Google Drive directly. Whatever you want to do, whatever code you want to write or anything is going to be stored directly on your Google Drive. So that way you can easily access it, either your friend's laptop or someone else's laptop next time you want to do it, or even on your phone next time you want to use it. Okay, so the first thing you should do using someone else's laptop is to come here. So you're going to see the profile you've set up, not here, right here, just beside the address bar. You're going to see this profile. This is my own profile that I'm currently using for this class. So if you click on this, you're going to see a list of profiles on the browser. If it is not there, that means there's probably only one profile yet on it. So you can actually add one to it. You can add yours, add a profile to it, then it asks you to actually sign in. So you can sign in your Google account, maybe your student email address, or anyone you plan to use for this class. You can sign in, just your Google account, your Gmail account, anyone you want to use. So you're going to just sign in with your account right there. Go that to enter your email and password and all. But I just want to show you how this works. So let me say I want to continue without one, and then I choose. So it's going to set up as though you have an entirely different browser, even though it is the same Google Chrome browser and you can access it from the same place. Alright, so I'm not creating a desktop shortcut for this. I just want it to be inside this browser. So I can add a name to it. Let's say I want to create a new profile and I want to call it my name, Jai. So that is all. I say it's done. So because I didn't open anything else, so it's set up an entirely new fresh browser for you to use. Even though it's the same Chrome, but it's a different profile. So if you want to go back to your friend's profile, your friend wants to use it, so they will just go back here and select the particular profile. So whatever you do here will remain here. You just close it, just exit normally. When you are done, then your friend can still continue doing whatever they are doing on the other profile also. So that's the way that works. So so anytime you want to use it, just go back here, open it, continue working. Your account is still logged in there, and then you can also set it so that you can continue from wherever you stop in history. So always be there for you to go back and continue. Alright, so that's that about that. And then we're going to be making use of Google Collaboratory. So it's actually a sort of notebook where we can write Python code and run it directly. So it's a lot easy, as you're going to see. You can actually add notes. You can add aside from the normal Python comment and all of that, you can add notes cells to your notes to the notebook. I mean the Google Collab notebook that we're going to be using. Alright, so so how do you access it? Once you've logged in as recommended, I said you should log in an account, a Gmail account there, so that whatever you are doing will be saved to your to your Google Drive as you do it. So just search for Google Collaboratory. So I've done that earlier, so it's still there. So I just Google Collaboratory. So this is Google Collaboratory. That's what you first see here, and then you go. Let's click on that. It's going to open the Google Collaboratory. It's already directly linked to your Google accounts once you have a Google account logged in already. So just start a new notebook. You might not have all of this except for Welcome to Collaboratory in your own account. So just start a new notebook. So it's going to load and give us a new notebook, a fresh notebook where we can write and run our code. Okay, so let's wait for it to load. And so you can see the title here of the notebook, so you can change it to anything with which you can anything that you can easily remember. So let's say I want to call this calculus calculus plus 1, calculus plus 1. Alright, so let's press enter, and that's all. So you have the name there, it's already automatically saved to your Google Drive. So you can look at it anytime you want to continue working on it. You want to edit something, you want to change something, you want to add a note, you want to add some code cells or whatever, you can always go back and do that in your Google Drive. Alright, so so we can continue right there. So this is a cell. You know what I mean by a cell? So you can actually put whatever you need to put here. Either you want to, this is a code cell, for instance. Display button, it's telling you to actually run the code. So it's by default that's Python 3 right here, so it runs your code directly. And with this, you don't need to install any library. If you want to make use of any Python package or library, you can just easily import it and use it. There is no need for installation of anything on your computer. You just need to open your Google Chrome and do everything we need to do for this course. So it is very straightforward. So even if your system has very low memory, you can easily do this once your system is able to open Google Chrome. Alright, so the library, the Python package we are going to be making use of here is what we call SymPy, symbolic Python library. So let me quickly do that. So let me say I want to add a note to this. I want to add a text block to this, so I'll cell to this. So let's say the first step, firstly, I will actually import the library. So import the SymPy library. So that's the first thing to do. Import the SymPy library. Alright, let's go. So that is that. So as you type it, you can see what it's going to look like here when you press shift enter. Alright, so if you want to give it some formatting, maybe you want to make it a heading, you want to make it bold, whatever you're doing, you see the result here. When you enter a code cell, you want it to look like a code, even though it's a notebook you're putting there, and all of that. So you can try that out, different editing styles, and see how it works. Alright, so that is that about that. Alright, so I want something like this. I'm just going to press shift and enter. Alright, so that's all. So I have that right there. So I want to import the SymPy library. So I think I should write this properly. SymPy library. Okay. Alright, so to do that, yes, you can do import SymPy as SP or whatever you want to do, or just import SymPy. But I'm going to do something like this. I'm going to write from SymPy, so just write it this way. Import star. So this star or asterisk or whatever you want to call it actually makes it possible for us to use all functions, methods, objects, and everything that comes with the SymPy library. We're going to use it as though they are default Python functions. Okay, so it's it makes the work very easy for us. If you don't do it this way, it means that in this notebook, anytime you want to use anything from SymPy package, you will have to call or make reference to SymPy first. For instance, if you wrote, let me give you an instance now. Let me put another code block. If instead of using this, if I used something like import SymPy, if I just said import SymPy, and then going forward, I just want to make use of a particular functionality in SymPy, I will have to make reference to it. For instance, I will have to say something like, okay, let me say I want to define a certain symbol. I will have to write something like SymPy dot symbol, because symbol is a function in SymPy. So I'll write symbol and I will put it the argument it needs. So I'm going to have to do something like this every time I need to make use of a function in SymPy. I'll have to refer to SymPy first, then put dot, then refer to the function. That's a lot of work. Another thing you can also do is you can say import SymPy as SP. That means you're using this alias, so it makes it easy for you to make reference to SymPy later. So instead of using SymPy.symbol, now you can now use sp.symbol if you want to make use of any function here. Alright, so those are examples, those are alternatives we can use, but here we're just going to use this from SymPy. Import star. Import star means import everything, import all the functionalities in SymPy into this notebook environment. So with that, we can use all of the functionalities in SymPy without having to actually make reference to SymPy like we did here. So once I do this first one, if I need to make use of symbol, I just call it directly as though it's a default Python function. So this is symbol. Alright, so that's what we're going to be doing in this course. So I'm just going to import SymPy. Alright, there's another thing I want to add there, but I don't want to add it first. So let's see something else. So let's this one load. You can see the state is initializing, connecting, blah blah blah. You see everything is now connected, and then it runs the code. Now it's completed. This is the time it took to complete the code. This is the time it completed the code. So it's done run. You can see the mark here, meaning that it has ended. Everything went fine. Okay, so there's another thing I'm going to add here, but I want you to know the reason we want to add it. So just like if you are doing calculus, you are going to make use of variables. For instance, if you are doing single variable calculus, we usually have to make reference to or make use of x. Let's say sin x plus cos x and all of those things when you want to define your functions. And so here we're going to be calling them symbols, not variables, because variables mean something else to the computer or whatever in terms of our computer science terminologies. Alright, so here we're going to define them as symbols. So if I want to make use of symbol x, I'm going to define it as symbol x. I'm going to say x is equal to this. So I'm going to define a variable x and bind that particular symbol to it that way. Alright, so we're going to do just that here. Another thing you can do is you can have something like this. For instance, let's say I want to have let's say a number of symbols. Let's say symbols A, B, C. I want each of them to represent alpha, beta, and gamma. So I can write ABC is equal to symbols. In this case, pay attention to the way I've written this. When you are using a plural form, this is small s, not big S, and then S is in front of it, symbols. Alright, then I'll put the symbols I want to attach to them here in a string. So I'm going to write this as alpha. Just normal way is write your alpha, beta, and gamma. Okay, so I've actually defined the variables A, B, C. I mean computer variables A, B, C. Now I have actually attached the symbols alpha, beta, and gamma to A, B, C respectively. So if I want to check any of them, I can easily try and find out. For instance, let me see what A, B, C is going to be. So let's run this code and see what it gives us. So you can see it tells us alpha, beta, gamma. Alright, but this is not what I'm looking for. This is not what I'm interested in. I'm actually interested in having it in symbolic form. This is symbolic Python. Alright, so it should be able to it is actually able to, it has the capacity to actually give us our results in symbols like we would have it in normal mathematical workings, like you are working in a notebook, a physical notebook now, or you're reading a textbook, where the text were written in maybe LaTeX or Word with normal mathematical terms and symbols, everything in place, right? So to make that possible here, we're going to actually initialize this. We say that it needs printing, so this will make our results, everything we need here to actually come in pretty print. I will call pretty print. So you see the implication of this now. So let me run this and then come back to run this now. So you're going to see the difference it makes. So instead of just alpha beta, that might now gives me the symbol. So this init printing ensures that it's giving me my result in fine prints or pretty prints. Okay, so that's what I need. That's what I want in this case. Alright, so the first thing first, import the SymPy library, then initialize this fine printing so that every other thing we want to do in this notebook is going to come in fine prints. If I do alpha, beta, gamma, whatever, it's going to come normally the way it should come. Alright, so that is that. And then since we are dealing with calculus, the next thing after all of this, the next thing is to actually define the symbols. Alright, define the symbolic variables. We're going to be using for our calculus. Alright, so since we're dealing with real valued functions, we must ensure that you bind each variable to real numbers. That is, say define each variable. Let's say you ensure that you define each variable as a real number. Okay, so we're going to ensure that we define each of the variables we are using here as real numbers. Okay, so I'm going to put this in bold, then increase the level just like some one I have up there. Yeah, that's that about that. So we're going to define symbolic variable. This is just for illustration to explain why this initialization was important. That was why I did this. Alright, so now we're going to do our proper calculus. So I'm going to define the variable x because I'm going to be using variable x all through. Alright, so I just need to define only one variable x. So I'm going to write x is equal to, that means that anytime I use the variable x, I'll be referring to the symbol x. So in this case, because I'm defining only one, I'm going to use this function. This is the way this SymPy has been programmed. Alright, so that's what we're using with capital letter, right? Yeah, so this is going to be capital letter, and I'm going to write x. So anytime I refer to or I call x, it's going to produce the symbol x. Okay, anytime I refer to the variable x, it's going to produce the symbol x. Alright, so again, I know that I'm dealing with real valued functions, so I should also include that this is a real number. And the way to do that is to say Python, this is actually a real number. I tell Python that this real is equal to true. So true is capital letter T for Python. So that's all Python actually needs. So now it actually saves this as a variable, so as a symbolic variable, alright, which is referring to real numbers. Okay, that is how to define a variable. So this is sufficient for what we want to do. You might be interested in playing around with more of this. For instance, you can have subscripts and superscripts, for instance, in a variable. Let's say I want to define variable. Let's say I want to have symbols like, okay, so let's just work with this. I'm not binding this to any variable. I just want to show you how some symbols work. Let's say I want to do something like alpha1, alpha. So I can do alpha. I just type alpha, then I'll type subscripts. So subscripts tells you, this underscore makes it a subscript. If I put double underscore, so you can always see the details here. This needs internet connection. This needs internet connection to work. Obviously, this actually has to load from the internet, and then your Google Drive is internet connected too. So So this gives you details about how you can define variables or different symbols and all of that. So so if it loads properly, if your internet connection is okay, this should come up, and then you can look at the details here and all of that. But the point I want to make is I just want you to know how to put, if you need to at any point, maybe later on you want to do something like this and you want to define a subscript and superscript, this is how to go about it. The superscript will be preceded by double underscore, the subscript will be preceded by single underscore. So let's see what this is going to give us. This is this is meant to be in quotation. I'm going to be in quotation, and then I'm defining just a single symbol. So let me use the proper one. I think this should work, but let me just do the proper thing. So this is the symbol I'm interested in. So Python gives me what I'm talking about: alpha, subscript 1, superscript 2. So that's the way basically it works. But this is what we're interested in, the symbol x, because I'm just dealing with functions of variable. Functions with one variable, single variable functions for now. Okay, so this is okay for what we want to do. So I've defined a symbolic variable. Then the next thing is now to define the functions that we want to use. Alright, so the next is what? The next is to define your functions. Define your functions. Alright, the functions we want to make use of. Okay, the functions of interest, the functions we're interested in studying, we're going to define them. Right, so we're going to put this here and say, let me give it that kind of editing also, bold, and so I want to define functions of interest to me. Right, and the way to define function is to just write expressions and then bind them to a certain variable. Alright, so let's say I want to define a function f of x equals x squared. So I've made a list of some functions here you might want to play around with and get their different forms. Okay, let's say I want to define a normal algebraic function. Let's say f of x equal to x squared plus 2x plus 1. So let's say, so I'm going to just write f, let's say f1. I can call it anything, any kind of variable. I just want to use f1. That's what's coming to my head. So x squared. So to do power, to get power in Python, you're going to use double asterisk. So let's say x squared is going to look like this. Then plus 2x, that will be 2 asterisk x. Then let's say minus 5. So let me write that here. That's my f1. So if I want to view what how SymPy is going to render this, I can do this and then just run this and see what it looks like. So SymPy just puts it in the symbolic form that I want it to be. So that's the way to define a function in this case. Alright, so I can define more functions. I can say f2. Let's say f2 is equal to, let's say, modulus of x. That's absolute value function. So if I want to do that, f under SymPy, I'm going to use a is capital letter, then b, and absolute value of x. So let's say absolute value of x. So I'll write it here just to view what this is going to turn out to be. So it's going to give me the absolute value function. That's it right there. The normal way you write it in your notebook. Okay, so I can define something else. Let's say the greatest integer function. The greatest integer function is called the floor function. Why is it called floor function? For instance, the greatest integer function gives you the greatest integer that is less than or equal to a certain number. Okay, let's say greatest integer less than or equal to 2.3. That is 2. That means you are taking that number to its floor. So that's how it came about, the floor terminology. Alright, so let's see. If I want to get the greatest integer less than or equal to 3, I'm going to write something like this. Let's say I'm going to call this f3. Greatest integer less than or equal to, let's say, greatest integer less than or equal to x. So I'm going to write it as floor x, the function that depends on x. So I'm going to write it as floor x. Just floor. There are no way to spell floor. So f3. So this will let me see what the function looks like. So this is the greatest integer function. You can see that this thing is not actually like a square bracket. Yeah, it's not wrong the way you were told, but it was written for you in class. So far it was defined what it meant was defined for you, so it's not a problem. But this is actually the conventional way it should be. This one only has this extension at the bottom. I hope you can see where this mouse is, right? Meaning that you are flooring a particular number, okay? And you can evaluate a function at a particular point. That's not what I'm interested in. This. You can evaluate a function at a particular point. To do that, you're going to do, for instance, if I want to get greatest integer less than or equal to 3.5, I can do something like this. I'm going to write f3, that's the function, and I'm going to write dot subs, like substitutes, subs, and I'm going to put in, okay, I want to substitute x equal to 3.5. So I want to substitute 3.5 for x. So the variable comes first, then the number I want to substitute for it comes here. And I'm going to play this around and see. So it's going to give me 3. Greatest integer less than or equal to 3.5 is 3. And you can do practically the same thing for any of the other functions also. For instance, I can get f of 1. I know if I put 1 here, it should give me 1 squared plus 2 times 1 minus 5. That's 1 plus 2. That's 3 minus 5. That's minus 2. So let's see. I can tell Python to do that for me. I want to say Python f1. Sorry. So I'm going to write f1 dot subs. Then I'm going to substitute x equals 1. So that's what I want to substitute here. So let's see what that gives us. Minus 2. So that's the way to evaluate the function at a particular point. So let's continue to define more functions. Let's say you have a trigonometric function, a function that carries over. Okay, let's look at a function that carries a square root. Look at this one. F of x equal to 1 over root sine x. So we can do that also there. So let me call that f4. Sorry. So f4, I'm going to write f4 equal to 1 over root sine x, 1 forward slash root. So that's given by square root sqrt, then sine x, sine. Normally we write sine, then x. Alright. Reason all of this is possible, all of these things are possible, was, don't forget, because we had imported from SymPy, we had imported all functions and capabilities of SymPy already. So these ones are now available to us as though they were normal Python functions. If you did not do something like this from the beginning, you would not be able to get these things like this. You would have to be recalling or making reference to SymPy at every instance. So in this case, there was no need for all of that. So it's Python naturally recognizes that we are using the functionality in SymPy. Alright, so that is that. So in this case, I've defined this function. I can view what the function looks like and just run this and see. So it gives me 1 over root sine x the way I want it to be. So if you want to define log, just write it normally as log also. So when you define tan, write it as tan. If you want to define arc sine, that's sine inverse, you can write a sine. So that's the way that works. For instance, if I want to do arctan, let's say next function is arctan of x. So I call that f5 equals arctan. So I'm going to write that as a tan to a tan of x. So that is that, and I can visualize this function to see what it looks like. So that is our arctan of x. That's what it displays. That's that. Then ln x. You know, ln is the same as log. I've told you in calculus, log refers to log to base e, not log to base 10. Alright, so if I want to write ln with x or ln 1 minus x or any of those, let's say I want to write something like this now. Sine x divided by x ln x. So I can define that function also. I can put in that quote. So I'm going to write f6 is equal to sine x. Alright, sine x divided by x ln x. So let me put that in brackets so that will be distinct from the numerator. X multiplied by the next log x. So I'm going to do that right here, and then I'm going to write it below so that I'll visualize what it looks like. So So that's that. It gives me sin x over x log x. That is that about that. So you can try out the others here. So I'm going to put a link in the video for you to look at the documentation for SymPy so that you can look at how to define some other functions. So you can do cube roots and all of that. Also, I think cube root is CBRT. If you want to do that, and then even if you can't remember that, you can just write raised to power 1 over 3 if you can't remember cube roots. Alright, so that's how to define functions right here. So you should be able to do that now. So what I needed to do is try and define these different functions. We'll look at how to do other things with this later on. For instance, you might want to get the domain of the function. Okay, domain. You can remember what the domain of the function is. And remember then, we would say that if you want to get the domain of a function, you try and exclude points or values of x that will give you a possibility of zero denominator, and also the ones that will give you possibility of having to take the even root or an even root of a negative number. Okay, you have to exclude all of that, and then for every other real number the function is defined, and that's going to give you the domain of the function. So you can get the domain of a function using Python directly. So it helps us to check those two conditions automatically, and it gives us the domain of the function. For instance, if I want to get the domain of the function f4, so let's quickly include this here so that you can do all of them together after this class. So let's quickly do that, and the way to do it is to actually make use of what we call the calculus package, still in the SymPy library, and calculus dot util dot continuous domain. So we're looking for the domain of continuity of that function, continuous domain. Then we put the function. So in this case I want to check for the function f4, so I'm going to put f4. Then I'm going to look for the values of x for which the function is defined. You know, we might have a multivariable function, so that's what necessitates this argument of putting x there. That means I want to check for the values of x for which the function is going to give me a real number. So if it were something like x squared plus chemical xy and all of that, I would have to check for I would have to specify also whether I want to check the values of y for which the function is defined or the values of x for which the function is defined. So that's all. Then what am I checking? What am I comparing it to? I want to check what domain am I really checking. So I'm going to check for the domain of real numbers. I'm going to write set of reals. So s dot reals is the way to do that. Alright. This is going to give me the domain of the function. So let's run this and see what it gives us. So it gives me the domain of the function. It tells me that this function can take in any any number between 0 and pi, excluding those that will be multiples of 2 pi and those that will be writable in the form 2n pi plus pi. So it's going to exclude, it has to exclude points that values of x that will make this denominator 0. That means values of x for which sin x is negative. So it has to exclude them. Yeah. So that's how we came about this and this. Alright. Sorry. Values of x for which sin x will be 0 will be excluded. Values of x for which sin x will be negative also will have to be excluded. This is how it came about, this exclusion. So you can think about what that is. So that is that. But you can also check for f6, for instance. I want to check for the domain of f6, just the same code. I'm just going to change that. So let's copy it and come here and then paste this and then check for f6. This is 6. So it's going to check for the domain of f6 this way. Every other thing remains the same. So it gives me the domain. It tells me that it's defined between 0 and 1, but 0 is excluded, 1 is excluded. Then from that it goes again from anything above 1 upward. It is defined. Why is that so? If you look at the function, you know that log is undefined for 0. If you have 0, you can have log 0. Log 0 is not going to give you a real number. It's going to give you something like minus infinity, which is not a real number. So you can only have log of positive numbers. Okay, so anything between 0 and this. And then again, if you have log 1, if you have 1 here, log 1 is going to give you 0, so we're going to have a 0 denominator again. So 0 cannot be there because that will give you 0 denominator in this. 1 cannot be there because that will produce 0 denominator right here. So that's to exclude those 2 points. And anything between them can be there. I mean, anything between 0 and 1 can be there, but 0 cannot be there, 1 cannot be there. Then anything above 1 again can be part of the domain. So that's exactly what Python tells us. So with this that we've done today, you should be able to you should know how to import the SymPy library. That's what we're going to use, and how to define different variables, and then how to actually declare to Python that the particular variable I'm using is a real valued one, so it knows that I'm dealing with real valued functions. When I define functions or expressions carrying the variable x, it automatically recognizes that I'm defining a real valued function. Alright, so so that is that about that. So please, I need you to work on these other problems. Just get the domain of these functions. Okay, get the domain of these functions. Alright, so you can pause and just write them out. So just play around with Python and get the domain of this function, and also try to reason about it, how reasonable it is for you or not. Alright, so in the next class we'll look at how to get a graph of functions with Python. Before we talk about how to get limits of functions and all of that. Alright, so that's the end of today's class. Thank you for tuning in. So I'll see you again next week.